Okay, so then we start. So first of all, I welcome you to this webinar on behalf of the Alice that you all are safe and healthy in the current pandemic situation. So Alice India Collaboration is organizing a series of webinars monthly basis. So people are joining still in the field of heavy ion polymers. And today we are having our first webinar. I would like to thank and convey my sincere gratitude to our respected speaker, Professor B.K. Srivastava, who kindly agreed and found time to be our first speaker of this series. To this audience, I don't think I need to introduce the speaker. Nonetheless, let me take this opportunity to say a few words in brief about him. So, Professor Dr. Dinesh, popularly also known as DKS, is currently Homi Bhabha National Institute of Bangalore. Professor Srivastava did his graduation in science from University of Allahabad in Training School of Bhabha Atomic Research Centre, BARC. In 1971, joined the Variable Energy Cyclotron project of the Department of Atomic Energy at DARC, Kolkata, later in 1979. Obtained his PhD in 1979 from University of. He has held many distinguished positions such as Raja Ramanna Fellow, Director and Distinguished Scientist at Cyclotron Centre, Amity University, NOIDA, Emeritus Professor National Institute. Is a Fellow of National Academy of Sciences, National Science Academy. He has held many visiting positions in the top-ranked international laboratories and universities such as Lawrence Berkeley National Lab and many more. Range of his research interest is also quite large, starting from the breakup of light nuclei. Some of his current research interests include electromagnetic probe, relativistic hydrodynamics and electric flow, etc. He has more than 160 publications, 100 talks, and 100 lectures, seminar, and colloquia. Professor Srivastava has been honored with several national awards for research and academic activities. As member board of scientific journals such as Physical Review C and Pramana. No, Professor Srivastava, since the day one of my research career in BCC, as a person, he is very kind-hearted, soft-spoken, accessible, and very supportive, especially to the young minds. Training, grooming, shaping, and inspiring the young minds is remarkable and is now becoming quite visible. To me, among others, this is one of the most beautiful. But today, it is our great pleasure and privilege to have Professor Srivastava with us as a speaker. Since this is the first talk of the series organized by the Alice India Collaboration, inviting the distinguished speaker, I would like to request the spokesperson of Alice India Collaboration. So,
thank you, Siddharth. Do you hear me?
Yes, we can hear you.
Okay. Thanks, everybody, and good afternoon, everybody. I hope you are all doing fine, but you are doing well at least. This happened, I think, in January 1st, a scheduled collaboration meeting in Aligarh, and we were all there, including many who are in the audience today. This we had trouble. It was the corona was not in that sense, but there are some other kind of trouble, and then we could not held our collaboration meeting at Aligarh on those 3 days, and there were many new students, first year students, and it could not be held. So we decided that means not to break the hearts of the students who prepared a lot to give presentation there. So we decided that we have all the presentations online, maybe after a week or so. So it was maybe after 2 weeks, we had 3 days, 2.5 days meeting again online, and there all the students, they gave their presentations. That was the time when this worldwide webinar or worldwide conferences online did not even start. So in that sense, we started these kind of online events even much earlier. And then, of course, you all know this corona thing came, and then everybody is now having conferences and meetings, all conferences and events, all collaboration as such here and everywhere, only on online. So in our last collaboration meeting, we decided that we have to have some distinguished speakers who will teach about the QGP field of research mainly, and we made a committee, small committee with that as a chair, and there are 2 students, I believe, junior members, and it is their effort that they organize this. They had long discussion how to do it. He is very thankful, privileged, and proud that Dr. Dinesh has agreed to meet as our first speaker series, and as that, needless to say that all of us in the community in India, we are all thankful and grateful to him for contributed in the field of research, especially to the students who to who is always accessible to discuss physics, discuss personal problems, discuss how to move next step. And so in that sense, Dr. Srivastava is someone who has made this pillar in this field of research in the country, and so I'm very thankful and very happy. We'll be hearing from him today, and I hope Siddharth and his team will have in the months to come. So that's all I wanted to say. Thank you, sir, and please start your talk.
Okay, so thank you, Subhasita. Now I would request Professor Srivastava to enlighten us. Sir, so you can take over now. So one small announcement, maybe we take up the question once the talk is over. And those who are listening in through YouTube, so they can write their questions. We will pick up some of them from there also. So you can now.
Can you hear me?
Yes, sir. Yes.
Yes.
We can hear you, and we can see the slides.
Okay. So thank you, Siddharth, and thank you, Subhasis. Have bright students in positions of power because they can say nice things about you and make you feel good. Just when the condition around the country starts making you very depressed. Okay, so as we were joking a few minutes ago, we have all been under house arrest since March. But poor quarks and gluons, they have been under house arrest, confined within protons and neutrons time of Big Bang. And Siddharth, Subhasis, Sanjeev Vasin, all these people liberate them from their confinement and studying them when they are not confined. Okay. I would like to dedicate this talk to the loving memory of Professor Dr. Shekhar Basu, tragically lost at a very young age, just a few days ago, and who did so much to support the collaboration at CERN and many other collaborations, international collaborations. Okay. Right in the beginning, let me tell some of the important observations. One important thing is that observation of quark is one of the most spectacular confirmations of quantum chromodynamics in strong interactions. Led to the creation of conditions of early universe a few microseconds after the Big Bang, the last occasion when quarks and gluons were free. It required the largest international effort ever mounted, with several thousand engineers and scientists in unison to build several accelerators and detectors, billions of dollars, computing techniques like grid computing to deal with the enormous bulk of data generated. Before I proceed, let me tell that at the request of, I prepared this talk for young students. I find that audience has very many veterans, Jujis, Vasis, Siddharth himself, and many others. And please forgive me for taking liberties with very accurate and trying to convey the idea. Okay. So all the talks on quark plasma normally proceed with this, that the universe started from a Big Bang, underwent inflation, all the quarks, gluons, photons, WZ mesons, etc., and even monopoles perhaps, were all produced 10⁻⁻10 seconds or so. We had a plasma of quarks, gluons, and photons, and some other elementary particles. In about 10 after about 10 microseconds, quarks and gluons, they came together and formed neutrons and protons and even mesons, decayed, of course, immediately. And then slowly, protons and neutrons came together and formed deuterons, then helium-3 and maybe even tritium and alpha particles. That's it. Then for quite some time, nothing happened. Okay, at about after about 3 into 10⁵ years, electrons and these nuclei, they combined, atoms were formed. Time that photons decoupled from this ionic plasma, and that is what you see as cosmological microwave background. Some of these nuclei elements, they came together, stars, huge stars, which in which some elements were also cooked, and these exploded in supernova explosions. And then we have the second generation of stars now here. And this event took place about 13.7 billion years ago. The importance of our work, or whatever work people are doing, is that using particle accelerators like RIG and LSC and create quark-gluon plasma in the laboratory. And you can study hydrogenization of the universe, hydrogenization of the quark-gluon plasma too, even though we don't understand it fully. And what is important to realize is that this is the last phase transition which we can study in the laboratory. and temperatures needed for earlier phase transitions like electroweak phase transition, etc., are far beyond the reach of mankind. We already know that we see are made up of quarks and leptons, and these are the bosons which are carriers of the forces between quarks and gluons. And you have the Higgs boson, which gives the mass. I don't have to tell this audience all this. What I would like to spend a little more time is, why was it necessary to introduce color quantum number? You see, once these three quarks were imagined, UD and S quarks, and you could immediately explain the structure of some of the lighter mesons and baryons. It was found that you have omega minus or three S quarks, all having their spin parallel. But you have delta plus plus, it must have three quarks, all of them having spin parallel, or delta minus, which should have DDD, their spins parallel. Now that is exactly what Pauli's principle will not allow you to do, because it suggests that you can have only one fermion. So the idea, it was solved by assigning an additional quantum number to these fellows, which was called color quantum number. It is not color in the sense, but it was just given a name, called color charge, and it was color quantum number in the green, red, and blue. And then baryons always had three colors, and meson, they were quarks and anti-quarks. And then you always had baryons and mesons, which were colorless, is white, which means colorless. Okay. So one other reason why you should have color is that if you look at E plus E minus going to mu plus mu minus, it is just one process, and you can study this very accurately. You can also study E plus E minus going to UU bar, or DD bar, or SS bar, or CC bar, or BB bar. Ratio of cross-section of production of hadrons and cross-section of production of muons in this process. You should get the ratio, which is charge of the quark square in units of charge of the muons. And that should have been 11 by 9 if all these processes were possible. But what you see is something like this, which is closer to 13 by 9, which corresponds to 5 quarks in 3 colors. So you need 3 colors to be able to explain this ratio. Or you can study the decay of pi 0 decay into 2 gammas, your PMD detector with many of you have worked. And its cross-section is given something like this. NC square, the process is QQ bar going to gamma gamma. Triangle diagram. And here the color factor should appear twice. If you don't have that color factor, you will get much smaller number. You get, theoretically, you get a width of 7.75. Experimentally, you have the value around 7.86 or so. Unless you put NC equal to 3, it would have been much too small. Okay. Now, the result of this introduction of color quantum number is that the coupling constant between quarks and gluons that increases log at larger distances. Since it stops the constant varies like this. By lambda square, or lambda is of the order 200 MeV. and beta 0 is 11 minus 2 by 3 NF, which is the number of layers which are which are effective right now. So if you look at it, the potential between two quarks, that can be written as alpha SQR by R. Small r, large Q, large momentum transfer, S tends to be 0. These two quarks will behave as free particles. And this is what you call asymptotic freedom. Large R, you can neglect the first term completely, and the second term just goes on increasing and increasing. If you recall the definition of potential energy from your BSc days, the potential energy is the energy to separate two particles to infinity. And then that energy here will come out to infinite because RdR is just infinite. Integral RdR is infinite. So you will actually never be able to separate two free quarks. Two quarks, you will never be able to separate. Infinite slavery, and because of which you don't ever see a free quark or gluon. And this is different from any other interaction we have come across. You know that the Coulomb interaction goes as 1 by R, the gravitational interaction goes as 1 by R, and things like that. This realization gave rise to, led to Nobel Prize for these three people, Gross, Wilczek, and Pollinger. As they may remember, they may know that Pollinger, I think, is no longer in physics, and after getting Nobel Prize. Now, if you take a hadron and you try to break it, how do you do it? You just hit one of them, one of the quarks, transfer a large momentum, then they will start moving away from each other. And remember that sigma r term, as the distance between them increases, that sigma r term goes on increasing. And a stage comes that the energy in the string is enough to more than the energy of masses of quark and antiquark. So it just breaks into quark and antiquark. And then you again get a, instead of one meson, you get two mesons. Quark and antiquark could not be separated. Same thing happens in the case of baryons. You hit one of them very hard, one of the quarks very hard, and you end up with lots and lots of hadrons. So when you try to break a hadron, you will end up producing more hadrons and not quarks. That is how you get this very famous cartoon. I don't like the word cartoon, but that is how it is called, where you have side and baryonic density on the x-axis. The dividing line is the one between quark-gluon plasma and the hadrons. And in Large Hadron Collider, you start from very high energy and you come down like this. At RIC also you come down like this. And the RIC energy scan combination. And one of the aims on which RIC people have done a lot of work is to try to find this point, the critical point, tri-critical point very accurately. And this will definitely be studied in a lot more detail at here, on which you people are working. Okay, you know this graph so well. So somewhere around 200 MeV or so, the energy density calculated from lattice quantum, lattice QCD increases rapidly. I mean, the energy density divided by T to the power 4 increases rapidly, which means that the temperature is not rising, but the energy density is rising, and that is the signature of phase transition, and that is where it happens. In the primordial quark-gluon plasma, the universe started from very high temperature and slowly went on cooling. And these are the degrees of freedom as the temperature dropped. and somewhere here was QCD phase transition at a temperature of around 100 Joule, which is what you people are able to produce in the in your experiment and study them. Okay. So how do you produce quark-gluon plasma? How to create quark-gluon plasma in laboratory? Sorry, excuse me. What you do, you take a gold atom, it has protons, neutrons, electrons around the nucleus. And then what you do is that you send this atom any cyclotron or pelletron, it happens. And then it will lose all its electrons. The atom becomes an ion. And then you accelerate this ion to near the speed of light. Another to similar speed of light. And they two collide, the quarks and gluons, protons and neutrons liberated, and you have a quark-gluon plasma, very high temperature. It's possible to simulate this process to some extent. One of the you can simulate it and study. So now somebody may ask me that you have quarks and gluons inside the proton and a neutron, and you have quarks and gluons inside a quark-gluon plasma. What is the difference? So on the left side, nuclear matter. You have half neutrons and protons. You have quarks and gluons in the protons. If one of the quarks here wants to go there, it can go only if the neutron, this nucleon as a whole goes there. It cannot go by itself. But here in quark-gluon plasma, gluons are free. Volume of the size of the nucleon, say, this fellow can go. This fellow can go anywhere inside that volume. In your experiments, you are producing quark-gluon plasma size volume are a little more. We shall come to that again and again. Okay. This is the relativistic Hebbian collider. Many of you have worked on it. Srivastava has worked on it. Siddharth has worked on it, and many others have worked on it. So this had several experiments. Phoenix, Phobos, Brahms. Initially, Brahms are gone. Phoenix also is gone. I think only star is remaining now. Phoenix is just that is what we just. And there you had these huge detectors called Phoenix. 400, more than 400 physicists and engineers from across the world worked. You had the star detector where many of you worked. Photon multiplicity detector. And there were more than 400 scientists there. And it had a rich harvest of results, some of which we shall discuss. The typical events at RIC, at Phoenix are here. This is only because of the angle of coverage. Every line you see here is track of the used in a TPC. And this is Large Hadron Collider, where you have a lead ion accelerated using a LINAC, which goes to low energy ion ring, then goes to proton synchrotron, then goes to source proton synchrotron, then goes to Large Hadron Collider. Experiment, ALICE, your experiment, CMS, LSCB, and ATLAS. Now, ALICE is purely fully dedicated to heavy ion research. CMS Atlas. Very good capabilities for heavy ion research. And so also LHCb. That is very convenient because then you can counter check many of the results. Okay, this is how the LHC is. I don't have to tell this to this audience. Okay. And you have trillions of protons racing around the LHC, and this old transparency. I think you have the increase in luminosity by factor of, and then huge number of collisions, millions and millions of collisions take place every second. Yeah, this is your Iris detector, the photon multiplicity detector here, built by VEC people, along with the number of all of you from Jammu, from IOP, from Jaipur, and this is the Muan arm, mostly by Aligarh people, and Saha Institute of Nuclear Physics. This is the Atlas detector, which you must have seen pictures many times. The CMS detectors again many times. I will come to the results in a little more detail, so I'll go through very quickly. In the lead-on-lead collision, this is the kind of event shape which you see. In particles, thousands of them, several thousands of them. Okay. What happens at the theoretical level? What happens in different stages of heavy ion collision is that you have initial states had two nuclei which are Lorentz current acted, like naans or thin chapatis, and they collide. There is a pre-equilibrium stage, short-lived pre-equilibrium stage, and then the medium is created, which expands and cools and hadronizes. And then after hadronization, this hot hadronic gas interacts for some time, and then it expands, cools, and then undergo the freeze out. When freeze out happens, a hadron going from one end to the other end will not encounter any collision. And if it does not encounter any collision, then its momentum and energy will not change. And that is why you say that the hadrons have just been frozen off. This is another picture in the same way, where you have the collision point, the pre-equilibrium stage, the quark-gluon plasma phase, could be mixed phase, the hadronic phase, and then the freeze out. So you see, you will never see the quarks and gluons. You will never see free quarks and gluons. You will see quark-gluon plasma, which will again convert into hadrons. Yes, you started with protons and neutrons, but you will get lots of hadrons of all kinds: pions, kaons, sigmas, omegas, rhos, all kinds of hadrons you will see. So how you can only measure them. So how do you know? How do you know what might form? So these are some of the main signatures of quark-gluon plasma. One is that we will see that very high energy density is produced, and that leads to jet quenching. We'll explain that. There is a particle chemical equilibrium of the particles produced, and we'll try to understand what it means. We will see that we see actually a thermal equilibrium, because of which there is a hydrodynamic behavior, which leads to azimuthal anisotropy in angular distribution of particles in non-central collisions. We shall see some other signatures of confinement. One is this anisotropy itself, which is called B2. Then the Gibbs-I yield, which is one of the old signatures of quark-gluon plasma. We used to think that its production will be suppressed, but now we know that at LHC, it can be suppressed as well as be enhanced. And then we have thermal photons and dileptons, on which our group has done some work. So first thing is to know that energy density enough to produce quark-gluon plasma has been produced. And the energy density can obtain from energy by volume, And one can calculate it from here, provided you know the formation time of the quark. Then I take it as 1 Fermi just to get a order of estimate, and this is called Bjorken estimate. And one can calculate the energy density, and it comes out about 5 GeV per Fermi cube. Why it is important? It is important because we know that the phase transition we are talking about takes place once the energy density is more than half a GeV or 0.7 GeV. We have much more than necessary energy density available for the quark-gluon plasma formation to take place. So first condition is definitely satisfied. And at LSC, the energy density using the same formulation is 12 to 14 GeV per Fermi cube, which means something like for the energy of 12 to 14 protons or neutrons is confined in the volume of 1 proton or neutron. So it's very high energy density, very high. You can also get the idea of the size of the quark-gluon plasma produced by taking a product of R out, R side, and R long, which appear in fine intensity interferometry, and the product of the three are a measure of volume of the quark-gluon plasma. And you can see that as the multiplicity increases, the red point here is Alice, and the other points are mostly from rich energies and even lower energies. And you can see that the quark-gluon plasma volume at LC is much larger compared to that at RIC. So at LSC, you have a plasma which has much higher energy density and which has much higher, larger volume. That helps you get very clean signatures with the cell C. So let's first come to chemical equilibrium. That all the particles which are produced in chemical equilibrium. All the particles, pions, kaons, omegas, lambdas, sigma, well, not sigmas, but cascades, etc. All of them are producing. Let's just assume. So, it will just be decided by two quantities, baryonic chemical potential and temperature, and nothing else. Now, if you know the particle ratios of just two particles, two of them, you can find out the mu and t. Determining that, you can predict the particle ratios are all of them. And it has been done for RIC and LHC. That these ratios are explained fairly satisfactorily over a very vast range of yield. Series from 10 to the power minus 4 to 10 to the power 3, including even light nuclei like anti-helium or anti-alpha or so. Now, what does it mean? Hadrons are produced in chemical equilibrium. But one can prove that if you wanted the hadrons to attain chemical equilibrium, the plasma or the interacting system should have lived for thousands of Fermi cube or 10,000 Fermi cube. We know from intensity interferometry that it never lives beyond 2-3 Fermi or 4 Fermi. So then it means that you can have a chemical equilibrium only if the reaction proceeded through a state in which quarks and gluons were interacting freely, and they were in a plasma state. In fact, using those relations, one can then predict what will be the temperature and the baryonic chemical potential at the freeze out for different initial conditions. 150 plus 50 GeV and 30 plus 30, etc. And the RIC energy scan. So you will go from this temperature to very high baryonic density. You cover this range. At FAIR and RICA, you will cover this range. Okay, so sorry, wait a second. So you can see that at Fair and Nika, at both the places, you can produce plasma at very high baryonic density and at relatively low temperature. This is the kind of energy density and temperature which one finds in neutron stars, perhaps. High, these studies are so very important because you can determine the equation of state of neutron stars. Jets. Consider two hadrons colliding. So there F1 and F2 are their structure functions collide at Q square, and then they fragment. So this is the cross section. This is the structure function. This is the cross section of the collision, and this is the fragmentation. There is a plasma, and going from here before it fragments, the quark or gluon can undergo several scatterings, and that it may lose energy. So this fragmentation function will change, and because of that, you will have what is known as jet suppression. You can see this again here. The PP collision produced, and both jets will surviving because there is no quark-gluon plasma formation. Yes, the collision, if one of the jets passes through the plasma, it will be suppressed because it will lose energy, and with the particles coming out from here will have very small momentum. So this is called jet quenching. This was seen for high PTG, pi 0, very strong suppression, factor of 5 suppression I see, up to very large PT. But then if you are a good experimentist, you should be skeptical. It was not because of some other reason. So what they did was to study the at RIC, you could not study P on gold, but you could study neutron on gold and gold on gold. So for gold on gold, they studied, and neutron on gold also they studied. In neutron on gold, they found two back-to-back peaks. Whereas in gold on gold, they found only one peak, telling that the second peak, which must have gone, corresponded to the jet going through the plasma, is completely suppressed. This was a real confirmation that jet quenching is taking place. This was studied in very great detail, high PT pi 0 suppression at various centralities. And then you can see here, as the centrality is increasing, becoming more and more central, more, and you are having more and more suppression. Ultimately 0 to 5%. And beyond 4 GeV, suppression is almost constant. Okay, so high PT suppression is taking place. Jet quenching is taking place. Can be used to calculate the energy loss of the quark-gluon plasma. Quarks and gluons in the quark-gluon plasma, as you can see here. The theoretical studies are reasonably successful with reasonable parameters to explain the data fairly accurately. Interesting is that even heavy flavors, I saw Santosh Das here, he studied that in great detail. Even heavy flavors like heavy quarks, even they lose energy. Tell that heavy quarks lose energy, people laughed at us. But I was trying to tell them that if you are seeing a heavy quark of 15 GeV or 20 GeV, what is its mass of 1 GeV? It is almost massless. So it should have similar energy loss as a light quark. But people laughed at us, but now, of course, it is all established that heavy quarks lose as much energy as light quarks. Okay, so this is confirmation of that. Then a most interesting confirmation came out from what is known as elliptic flow. proceeds like this. Sorry. क्या हो गया भाई? Yeah. So two nuclei to collide with each other, head-on collisions, slightly off-center collisions. The reaction plane at the zone, this overlap zone becomes, and the pressure gradient on this side will be higher, the large axis side will be smaller, and then the particles coming out at this, from the small axis side will be pushed out with a lot more momentum compared to those at the larger side. Fine, that should give rise to azimuthal variation. But while talking about this, I have cheated you. I told pressure gradient, but how can you have pressure unless there is temperature? How can you have pressure gradient unless you have flow? You cannot have a temperature unless there is a lot of collision. So if you are seeing this, you are seeing that system which developed a lot of pressure because there was a very large temperature and there was a pressure gradient formation. That is the reason that elliptic flow is considered a very important conformation of quark formation. So what it does is to isotrope coordinate space is converted to anisotrope momentum space, and you have the Fourier transform of the momentum distribution E d cube by d cube p, and you can take the coefficients, and those coefficients are determined, and these are not small; they are very large. But what was important to realize is that there was a big separation between pions and protons. And this was very accurately explained by hydrodynamics. This was the first time that hydrodynamics explained the PT distribution as well as the V2, the elliptic flow of low PT hadrons. How do you know that the flow developed? When did it develop? What people saw that, and they started plotting the V2 for pions and K mesons or phi mesons and protons and neutrons. They, after, in the beginning they were similar, but after some time they separated. They thought that it is mass effect. Then they had D mesons. D mesons followed the pions. And then people came up with this beautiful idea that they took V2 and divided by the number of valency quarks. And they took the kinetic energy of the particle, transverse kinetic energy, and divided it by valency quarks. And then they found that there is perfect scaling. And this can only mean that you have a phase with quarks as dynamic degrees of freedom developed. This was another very robust signature of quark formation. Then hydrodynamics we were using, and initially people all used ideal hydrodynamics, but very soon it was realized that one can do the viscous hydrodynamics, and here was the viscous hydrodynamics calculation. Sorry, and why it is not working, I don't know. Okay, so if you have the viscosity 0, it goes like this. Viscosity is 1/4 pi, it goes like this. 2/4 pi, 3/4 pi, and there are some reasons to believe that eta s should be of the order of 1/4 pi, and then you find that eta by s is 1/4 pi. And in fact, it is found that quark plasma is the lowest and most perfect fluid of all the fluids known in nature. And quark plasma was found at Rick, and then the viscosity was determined to be so low, they said that Rick Brookhaven serves perfect fluid. You can have photons photons have the advantage that photons are produced from annihilation of quarks and gluons or from hadronic reactions. They tell you the temperature. If they're coming from hadronic gas, they should have temperature like coming from quark plasma, they may have that kind of temperature. There may be 3 equilibrium states, there are the proton photons, and there may also be jet-free interaction. And all these processes are possible: quark-gluon scattering, quark-anti-quark annihilation or fragmentation, or even you have annihilation, scattering, you have hadronic reactions. Later in great detail, and then you can do a detailed calculation about the hydrodynamics. You can also have the interaction of hard scattered parton with dense matter to get jet photon conversion as an external probe. But this turned out that even though it is large, much larger than thermal contribution, it is only a small part of the plant part, and therefore it's not very easy to figure out. But perhaps at LSC or at FCC it will be seen more clearly. The direct photons have been measured at RIC and LSC, and they correspond to very high temperatures, at least 221 MeV at RIC and at least 304 MeV at LSC, which is the highest temperature anywhere in the universe. But this is something which I love. You see, in the nucleus-nucleus collisions, we have neutrons and protons. They're continuously moving. So no two collisions are going to be identical because the positions of neutrons and protons in all the nuclei are constantly changing. So all the collisions will be different. So these will lead to what are known as event-by-event fluctuations. And those event-by-event fluctuations can have hot spots. And it is important to include them in order to get accurate description of spectrum. And this also gives rise to, elliptic flow. You can have elliptic flow if the overlap region is like ellipsoid. You can have triangular flow, and in fact, you can even have directed flow if you have a collision of something like copper and gold, and you have asymmetric system. These things have been seen for hadrons. What I want to tell is that we made a first prediction. Rupa Chatterjee made first prediction that you should see elliptic flow for photons. And yes, elliptic flow for photons had been seen at RIC. But the data is almost always factor of 2 to 3, both at RIC and at LSC compared to the theoretical predictions. All the theoretical predictions using various theories are factor of 2 to 3 smaller than the data, and we have not yet been able to understand it. Okay. Same thing is happening with V2, V3 also. Triangular flow has also been observed. And here also, I have not shown the experimental data. Here also, the theoretical predictions are smaller by a factor of 2 to 3. The directed flow has just been predicted, and it has a very different nature. It is negative, and at higher PT is positive, which is very different nature from V2 and V3. I hope that some of you will measure it. Okay. We had also predicted that thermal dielectron elliptic flow will be seen, and I understand that STAR people are doing this measurement, and we should have some of these results soon. Okay. This is JEPSI. This is an ideal probe. It would have been ideal probe. And that was the reason Helmut Satz and Matsui, who proposed it right in the beginning, got so much importance. It's like this. There is a probe. If it goes through a vacuum, nothing will happen to it. If it goes through a hadronic matter, maybe some of it is absorbed. And if it goes through quark-gluon plasma, a lot of it is absorbed. Okay. So Jepsi production, state of CC bar, it has several excited states, psi 2s, chi C, and Jepsi. What is important is that if the temperature is less than Tc, then this can, you will see all three of them in the data. If the temperature becomes close to Tc, this one is suppressed. And you see only chi C and Jepsi. If the temperature becomes a little more than Tc, and you see only Jepsi. And when the temperature is much more than Tc, then Jepsi vanishes. And then you will see, that is why it was said that you will see successive suppression of these states. And therefore, it was considered very valuable. Okay. So it could also be a temperature, etc., etc. But then there is always a problem. You consider two collisions, one at RIC and one at LHC. At RIC energy, you will at most have just one CC bar pair in an event. This CC bar can come together and form Jepsi, or they can drift apart and make DD bar. If it makes a Jepsi, you will see Jepsi. If it becomes DD bar, you will not see Jepsi. Same thing happens here at LSC, but here you will have several CC bar pairs produced in the same collision. Now, even if these Jepsi, this CC bar and this CC bar, they all drift apart and they are all suppressed, Jepsi production is suppressed. What can happen is that C and C bar, C from here and C bar from here, they can join, or C from here and C bar from here, they can join. So there may be regeneration of Jepsi. So what was suggested is that at RIC, you see a suppression, but at LSC, you should see a suppression, then you should see enhancement. And in fact, it was seen. So suppression at LSC, you see a little enhancement. So this has to be studied in greater detail, find out which part of PT spectrum is for suppression, which part is from recombination. This can be done, and this subject matter of great study. Okay. Upsilon is a lot more cleaner, and you see that the extent of suppression both at RIC and LSC are more or less similar. We'll also study collision of photons, because if you have two large nuclei at such a high energy, they are Lorentz contracted, they pass through each other. They will have a very strong Coulomb field. What is Coulomb field? It is just photons. So you will have photon-photon collisions. And this is being studied in great detail. Excuse me. You will also have a very strong production of a very strong magnetic field, but that is very short-lived in the beginning. But you have such a strong magnetic field that will leave some effect, and that is a subject matter of great study now, and it can actually affect the flow also of particles, and positively charged and negatively charged particles will be affected differently because of this. That should be studied, and it is being studied. There has also been, because you are talking about a fluid, right? So if you have fluid droplet and two fluids collide, two quark-gluon plasma, two quark-gluon clouds have collided and formed this fluid, there may be local whirlpools. Lot of angular momentum. That angular momentum can couple particles which are coming out. It gives rise to polarization of lambda particles, which has been seen at RIC and not seen at LSC. And that remains a subject matter of very interesting study. Okay. Fine. Plasma is formed. That is formed by shattering of color glass, about which I did not talk about it. Talk about at all the color gluon condensate. How does it thermalize? No theoretical calculation can tell you, can give you a thermalization at such a short time of 0.2 Fermi or 0.3 Fermi over C. Then how do you get strongly interacting quark-gluon plasma? How do you get thermalization? How do you get strongly interacting plasma? One thing which has not remained clear so far is that how do fast quarks and gluons and heavy quarks lose energy while traversing plasma? Do they lose it by collision alone, or they because of radiation, or both? At least for heavy quarks, this would be a very interesting study. What is the temperature of the plasma? Of course, we have measured it using photons, but can we study it in a little more detail? The suppression and regeneration has to be studied in greater detail with a lot more accuracy, which is being done. And you see, you are always measuring hadrons. There is no theory of hadronization so far. We have only models, recombination model, fragmentation model, and string fragmentation of the jet fragmentation, string fragmentation, and recombination. But these are models. You assume that there was a quark going and it produced a pion. And this was the function. You fit that function to the data. That is not theory. We have to develop a theory of hadronization. And that will take quite some time. The order of phase transition, now it is more or less settled that at RIG, it is most only a rapid phase crossover, but where is the end of the crossover and where is the beginning of the first order phase transition? These are some of the old questions which have not yet remained answered. Okay. But let us come back to your hair. A huge amount of brouhaha was created when Higgs boson was produced, was detected. But if you look at the mass of up and down quarks or strand quarks, you find that up quark has a mass of about 5 MeV, down quark has a mass of about 10 MeV, strand quark has a mass of about 150 MeV. But inside a neutron or a proton, these flows have masses of about 300. The constituent quarks have mass of about 330 MeV. This has a mass of about 350 MeV. And as we know, all matter we see, all the visible matter, all the baryonic matter in the universe, even though it is a small part, is made up of only neutrons, protons. Electrons have almost to these flows. Higgs boson are responsible for just 5% of the mass. The rest of the mass is created by QCD interaction. And that is what we are going to study at FAIR. Right? You know FAIR, I don't have it to explain this. And you know the CBM experiment, and you know the CBM, which the muon chamber which you are going to make from Kolkata, and so many other things have been made by India. You have equal partner in FAIR, and that is a great opportunity for young students, which was not available to us when we started our career. And then this will be the real big thing if it happens. The future circular collider with a ring size of 100 kilometers. This is LHC. And this is FCC. This will collide proton and proton at 100 TeV and lead on lead at 39 TeV. It will start with E collision at 90 to 350 GeV to see if there is something, structure of Higgs boson or excited states of Higgs boson. Are there other states of Higgs boson? How does it decay, etc. Okay, so this work on this has already started. I hope and pray the beginning at least of this FCC, and you people get an opportunity to work on this. And then you people are very lucky there because India is now associate member of CERN. You can go there as an equal, you can propose experiment, you can even get jobs there and work there. And which all happened because of Dr. Basu. Process started much earlier, but ultimately it was completed in time, which opened such a nice situation for all of you. Okay. So you see, the coming years are going to provide answers to all kinds of questions, perhaps raise many more, especially for compressed baryonic matter, which will be studied at FAIR and NICA. I did not tell you anything about NICA, which is being made at Dubna. They keep inviting us to join their collaboration, but how many collaboration can be joined? Okay, and also the FCC. There is also a spin rig coming up, which will give you information about initial state and also the spin of protons and neutrons. But on this occasion, we are part of team. Earlier, beginning our career, we would read about wonderful experiments. I wish we were part of this collaboration. I wish we could do it. You people are part of the team, not mere spectators. So I wish you very great harvest of bountiful results in days to come. Again, and giving me an opportunity to meet so many of my old friends and students. Thank you very much.
Okay, thank you, sir, for this nice and comprehensive talk. Steps of QGP, facilities required to collide heavy ions, and then conditions under which QGP is created, various profs required to explore it, properties associated to it, and also giving hint about the future direction. So now we open to take. So I already see there are 2 questions in the chat box. So those who want to ask question, they can mention in the chat box, and then we can take up one by one. So first question is from Aditya Prasad Das. So Aditya, you want to speak yourself?
Yeah, thank you.
Yeah.
Thank you, sir, for this nice talk. Sir, you mentioned like the measurements of the photon flow. You showed the plots for directed flow, and you said that these are preliminary results from RIC. So where the
हम retire हो चुके हैं. I don't get at the institute where I am working now. We cannot access any journal. Okay, I cannot access any journals. I cannot get the latest results, but those results are now no longer preliminary.
Yeah. Okay. So, what I was trying to ask is the directed flow results. These are like, why is it always difficult to get the directed flow? Because flow signals are very, we find a lot of results there. It's basically because of the initial state anisotropy. I understand that, but still directed flow is very less.
Yeah, it is a weak flow. It is weak, but you people are very imaginative and very capable. I have found that theoreticians can come up with the idea experiment, always find a way to measure it. It has been measured not at for photons. Some preliminary results I understand for photons are also available. In fact, we made the prediction because some people were seeing some hint of elliptic flow for photons, very small hint they were seeing. And that is when they approached Drupadi to make the prediction.
Okay.
Yeah.
Okay.
So it is seen.
Thank you.
और अभी काफी टाइम है भाई. You people have to do much better experiments than Siddharth and Supriya and Anjuli and Subhasis have done. You people have to do much better experiments, much better accuracy. That is how we will feel proud of you. Yeah. Please.
Thank you, sir.
Okay, so next question is by Professor Raghunath Sahu. Raghu bhai, so could you please ask?
So as I mentioned, it is just random
No,
thought.
for that I have. What is difference between Raghu bhai and Raghu da?
It is a phase transition from Odisha to West Bengal.
Yes.
Okay.
Where you are sitting, so.
Okay. Go ahead.
So as I mentioned in the chat box, it is a random thought. It may not be a question, but just to invoke the discussions. So the question is the following: can we have a single theory with a high energy crossover transition and a low energy limit of which or low baryochemical potential limit, a high baryochemical potential limit? Transition with so I know it is a complex phenomena involved and many degrees of freedom playing a role. It may not be possible like our grand unification. It may not be possible to construct a single theory with a first order phase transition, critical point, and second order phase transition or crossover transition. But is it possible to think like a dream is doable or no?
Well, there are two ways of looking at it. You see, in the beginning, you will remember that during SPS days and also during early RIG days, all the hydrodynamic calculations were done using a first order phase transition. And also some hydrodynamic calculations were done at lower energies at SPS. But there it was an assumption that hydrodynamic works. It was an assumption that there is a thermal equilibrium. So if you have assumed a thermal equilibrium and assumed a quark-gluon plasma with a certain baryonic chemical potential at a certain temperature, you can assume a first order phase transition and do the calculation. And as the mu keeps coming down, the first order phase transition will somehow vanish. It happens. There is nothing very great about it. But that is a very strong assumption. Lattice QCD calculation for finite baryonic chemical potential is making some small progress. For small mu, it is possible to extrapolate the results, but larger mu results are not at available. So you don't have any guidance, not enough guidance from lattice QCD also. I am more hopeful in the ingenuity of experimentalists as well as of theoreticians. And I'm quite sure that in a few years' time, when lattice QCD, with the increasing computing power, it may become possible to get lattice QCD calculation for finite baryonic chemical potentials a little more accurately. Of course, there are a lot of QCD-inspired field theories which work reasonably well for hadronic gas and also for QCD, but those are not extremely accurate as yet. And a theory is a theory, and model is a model. We always say Nambu-Jonar-Lasagna model, right? It's not Nambu-Jonar-Lasagna theory. So theories have to develop, and we have time. After all, what will your grandchildren do? You have to leave some problem for them, right? Other than climate change.
I mean, the same theory, critical endpoint will be a byproduct. Do you think that?
Yeah, it should automatically come.
Okay. Okay, thank you, sir.
Okay, so now we have a question from Professor Pradeep Sahu. Pradeep sir.
Good evening, sir.
Good evening. Nice to see you.
Nice to see you in the
Well, nice to hear you. Actually, I am not seeing you.
Nice to hear you. Yeah. So I have very simple question. You have showed some of the slide. Your net baryon versus different energy of experiment. You said somewhere actually.
Not experiment. Those are predictions.
Yeah. So somewhere you said that in fair it will be the highest net baryon density.
Yeah.
But what I saw that the highest baryon density will not reaching to the nuclear matter. Am I correct?
That is at the time of freeze out.
At the time of freeze out. So it will never reach the nuclear matter density, I guess.
Yeah, perhaps, but there are at lower temperatures. Yeah, well, it is not. You are not seeing that is the largest baryonic chemical potential, which is this is John Clemens says what they did was that they calculated T and mu for number of systems at different energies, and then they fitted a curve, and then around that curve they took T and mu.
Okay. Okay. So that's what my doubt.
Temperature versus root S and mu versus root S, and then they just took the combination.
Yes. Some of the simulation model, as far as my knowledge concerned, is that it has gone to even 2-3 times the nuclear matter density. Chemical, baryon chemical potential.
Yeah, but you see, my personal feeling is that I always feel a little worried about these things, that till there is assuming here that there is a thermal and chemical equilibrium.
Okay.
At lower energies, I'm not so sure that it will be true. But I don't know how, at least given thermal equilibrium and chemical equilibrium, you can proceed. You don't have that, and you have only URQMD or one of those things.
Yeah.
And again, you will be fitting to the results there to an assumption of thermal and chemical equilibrium.
Okay. Okay. Understood.
So,
Thank you, sir.
Siddharth, can I add to the discussion? I have a small point here.
Yeah, sure. Go ahead.
So, just sir, if I remember correctly, in the paper of Androff and Clemens, this one has been taken as E over N as 1 GeV.
Yeah.
So, at very low energy, what Pradeep Bhai is talking about, so this condition of freeze out will work or do not work, that is also a question. At very low energies, like very high baryochemical potential.
No, this condition is found to work at very low energies. It is found to work even at SIS energies.
Yeah.
So, okay.
It has been found to work.
Yeah.
So I was just keeping
all that formulation E by N being 1 GeV means is that as the center of mass energy increases, more pions are produced, more and more mesons are produced. So the number of meson versus baryons, and that is how E by N remains constant. Yeah.
So high energy is becoming meson dominated freeze out.
Yeah. High energy is meson dominated, low energy is baryon dominated.
Yeah. Okay. Thank you, sir.
Thanks.
Okay, so we have 2 more questions from Aditya and Meenakshi, but before that I have a question from YouTube. This question is from Sayak, so I am reading the question. He is Sayak Chatterjee, a student working in CBM experiment at Bose Institute. So his question is, sir, as you have mentioned that FCC will help us in more details. So I want to ask about the gravitron. we can have that in FCC, and if no, then what is the main restriction for that?
The answer to this is that I don't know. My frank answer is that I don't know, but I don't think that will chance here, because even in the collision of neutron stars, people have not yet talked about gravitons. I don't think that here you will. I mean, if you see them, very, very, very nice, but before that you have to find dark matter candidates. Before that you have to find what is dark energy, and whether you have extra dimensions or not, for which there is no proof so far. See, if you see some of the early talks when the LSE was being under construction, beautiful concepts, black hole production, the collapse of extra dimensions, etc., all kinds of things. None of those things have been seen. Or maybe at higher energies we start seeing them. I don't know. No.
Okay, so Sayak, I think you are listening in YouTube, so it might have answered your question. So now next question is by Aditya Prasad. So can you ask yourself?
Yeah, so my question was related to the previous question, calculations in the future colliders like the FCC, etc.
Which calculation?
String theoretic calculations.
If you can do that, that will be great, because so far nothing of string theory has been verified except for that little eta by s being of the order of 1 by 4 pi. Is Santosh there?
It's left, I guess. Just
Yeah.
a while.
They made a prediction for energy loss of quarks, which was, I think, found to be incorrect. They made many predictions. None of them have been seen. Only eta by s being very small, that had been seen, but that is a kind of correspondence to do with theory. String theory, yeah.
Thank you.
Okay. So next question, Meenakshi. So can you please unmute and ask? Meenakshi Sharma.
Yes, sir. Thank you, sir, for the nice talk. Actually, I just want to ask that we have discussed that it's still a puzzle that how in such a small time equilibrium is attained in heavy-ion collisions. So what are your thoughts in QGP-like hints in even small systems?
I have no idea. If I had an idea, I would have done it. We have seen in our part-on cascade model, could use perturbative QCD, but that perturbative QCD could be used if it was more than 2 GB. The rigorous practitioners will laugh at you if you are using QCD at 2 GB. Below 20 GB should be used. It's reliable. But we used it till down to GB, and we did not find. But at momentum transfers of 1 GB, the interaction is no longer perturbative. So we don't know what are the cross sections. So there is no way to calculate it, only theoretical calculations. Some other methods have to be invented to study how the temperature, how the thermalization is attained. I don't know how it is being done. I have also been out of touch a little bit, I must say, but I have not seen anything. I still keep checking on the newer results. But it is not yet known how the thermalization is achieved so quickly. There's no theory using perturbative QCD, which is all that you can trust, which can give you. Yes, Simon, there is a kind of model. It's called self-screen parton cascade model. In this, what we assume is that we assume that the partons, the high PT partons will produce first and low PT partons will produce later. So high protons are produced and they create a atmosphere where you can calculate the device screening and use that device screening in the scattering potential of two partons. And as in the beginning, the device screening radius will be large, small, and then as the more and more partons are added, it will go on increasing. So supposing you can produce enough number of partons to have a device screening which is sufficient, then you can use a device screen interaction potential. And that gives some kind, a little but approach to chemical equilibrium, thermal equilibrium. This used to be very fashionable at one time. I think there is old by Mueller and Wang and Scola, I think, where they did this. It's called self-screen parton cascade model. But I do not know whether they followed it up later or not. We had started doing it, but then my time was up. Way in which you can proceed. It is a model, but a reasonable model. And it may actually work at LHC energies. Yeah.
Okay, sir. Thank you.
So maybe I can just add a similar question related to this. Sir, if you remember in 2000, I think in 2008 or 9, in VCC talk, when I was talking about the flow in PP kind of system, then there were a lot of discussion in talk. But nowadays, experimentally, it is seen that features which are which are related to heavy ion collisions are also seen in PP-like system, in PP systems.
Yes.
That when we go to high multiplicity events, then at least from the jet point of view, the composition of the jets changes because the fraction from gluon and quark jets are different. And you really see a change in the jet properties, and that's not because you created something. That is in model, not in data. I have not checked in data. That is not because you created something, but it is because the composition has changed and the quark and gluon jets behave differently. So
that's very nice. I have been waiting for such a result. I have been waiting for such a result. Thank you. I'll look it up. Very nice.
Okay. So now my question is how one should use the PP as a reference when we already see some kind of behavior which we already see in heavy ion.
Yeah.
How reliable it is.
It is no longer the gold standard. PP is no longer the gold standard. You can, that RCP which people used to use, right? You remember that central versus peripheral?
Yes.
That is the only way to do it.
Okay. Thank you, sir. So I have one more question from YouTube, and this is from Ajit Kumar of VCC. So he says, want to ask a question. We try to explain the data with different models. Why so many models? Is it possible to have one model which can explain roughly all data?
Oh, that will be as working theory as you can think of. You see, different models have different assumptions. Some of the assumptions may be valid, some of the assumptions may not be valid. Look at Pythia, for example. Pythia considers the scattering of partons at high PT. I think PT0 is taken as 2 GeV or 4 GeV, you can choose the value. The high PT scattering between partons as perturbative QCD. And then those partons which have high PT fragment into hadrons. Interaction among the partons is calculated using string theory, not the string theory of grand unification, but string theory, what they call it. Yeah. Then they hadronize by breaking off strings. So you have two different. Temperature does not appear anywhere. Equilibration does not appear anywhere. Flow does not appear anywhere. None of these things are built in. But look at AMPT. It takes initial conditions from Ising and then assumes that hydrodynamics is valid. So this assumption that hydrodynamics is valid is an assumption. Because at some stage, hydrodynamics just takes over. So different models are having different initial conditions, different assumptions, and different approximations in proceeding. And that is why you have so many models. It depends. If you are looking at high PT results, you better use PT and not hydrodynamics. If you are looking at low PT, where flow is important, you better use a hydrodynamic calculation or a calculation which has hydrodynamics built in. So that is how it proceeds. URQMD, for example. It just parameterizes all the cross sections of hadrons, hadron cross sections, and then as a function of root S, and then uses that. Those parameters, sometimes those cross sections are obtained by sheer guess, by using counting rules, etc. All kinds of tricks are used. Those cross sections are not measured. Those cross sections are not known. There is no way to measure them. How are you going to measure? And at the moment, it is not very easy to measure those cross sections. How do you measure the cross section between cascade and pion scattering, for example? You need to have a beam of pions and a beam of cascade. Is it possible? Just assume that cross section. So you are making those assumptions. As long as those assumptions are reasonable, may remain reasonable. So the number of models depends upon you are going to concentrate on. Ajit, does that explain your question?
I hope Ajit is in YouTube, so he can't speak. I hope he listened. So he heard.
You can tell them that they can write to me. Yeah.
So are there more questions? So looks like no more questions. So
I have one question.
Yes.
So, sir, what is your verdict about equilibrium in experimentally? Means when can we say yes, equilibrium is achieved? Because all those mass ordering and everything has been seen. Hydrodynamics is applicable very well. So at least experimentally, when can you see with which observable that yes, equilibrium is achieved? Is there any?
Actually, one of the I don't know how to do the best signature. One of the signatures of equilibration is momentum distribution. in the rest frame of the fluid. And we are assuming that all the time in all our hydrodynamic calculations, etc. So I suppose if hydrodynamic calculations are explaining the data, maybe, but nobody has as yet done a calculation. Is not assumed. For example, in URQMD equilibration, you don't assume thermal equilibrium, right?
Right.
Hoga nahi hoga. But that also explains large part of data.
Yeah.
And URQMD fellows hate this particle ratio because they think that it is somehow simulating the result of various decay channels. So it is very difficult. But flow, temperature, and I would like to look at some of the variables which are to the chemical potential of quarks.
Okay.
You may get that dielectron production from quark and anti-quark annihilation.
Yeah.
That may be a good thing, but whether we can see it separately or not, I don't know. But now that you can charm decay, correlated charm decay at RIC and also at LSC, there is hope that you can see quark anti-quark annihilation. And that will be lambda q times lambda q bar. That would be very interesting other way if it comes out. Because that will tell you the quarks. In fact, we know for quite some time that gluons thermalize earlier than quarks. So it should have some kind of signature on quark anti-quark annihilation seen by dielectrons. Let us hope that something comes out of that.
Okay.
But you know that at SPS energies, the flow, hydrodynamics predicts very high flow, which is much, much less than what experimentally it was observed. Right? And that is why hydrodynamics was not fully trusted at SPS energies. So then where do you go? Yeah.
Okay.
Okay. So
Okay.
I am waiting for you people to provide answers to many of these questions.
Thank you.
Okay, so it seems there are no more questions. We also had a very good long discussion of about more than close to 2 hours. There is also Sharon to. Before I finish, I would like to thank everyone for joining from the different part of the country and also from abroad. I saw Tapanga joining from CERN, and I especially thank my colleagues Pratay Das from Bose Institute, Vikas Sumeria from Jammu University, Shreya and Sarkat from Bose Institute for helping me out in organizing this, because there were two things going on, this one and plus the YouTube live streaming, and also we received few questions from YouTube. So,
I hope you were able to hear me properly.
Yes, sir, because Ajit also replied that he listened to you. He heard your answer.
Oh.
YouTube. So it looks that is okay.
Yeah. Okay, well, thank you very much. Thank you all. Thanks all of you.
Thank you, sir. Thank you, sir.
Here, many of you.
Yeah, thank you.
Those happy days. I hope that it all comes to an end. Thank you very much.
Okay, bye.
Thank you.
Thank you. Bye.